Okay, do you have any questions before we start? Which one? This one? Okay, let's redo this question. Now the question is, we have these two shells, like your homework problem. One outer shell. And then you have the inner shell. These are all spheres. And then inside you put some plus Q charge. Now you take this point P1 and then you have this point P2. So the question is, what is the potential difference between these 2 points? Delta V, let's define it as V of P1 minus V of P2. Now the definition of this potential difference was equal to the integral from P2 to P1 of E dot dl, minus, with a minus sign. This is how we define the potential difference between the 2 points. Now, how do we go from P1 to P2? Well, you just choose any path that you like. Now, the thing is, for the electric field, this integral should be independent of how you go from the initial point to the final point. So we can just choose a path, let's say from, this is our point P1, this is a radial line that goes through the point P1. So we can start over P2, move to this radial line within the conductor, and then move along this line until P1. So this is how we can go from point P2 to P1. One possible way. I mean, you can choose any way you like, the result should be the same. The thing is, along this path, it will be easy to calculate this integral. Now, how we calculate this line integral, we just divide this path into very small segments. Here we take this dl. This is our dl. dl is in this direction. This is our dl for one segment here. The electric field within the conductor is 0. So the integral receives only contribution as we go from this point to this final point. And it doesn't receive any other contribution from anywhere else. So we should only consider the contribution to this integral along this segment, which is out of the conductor. So along this segment, this is a typical dl. I'm just enlarged this very small dl. Well, the electric field is on the other in the other direction. This is the direction of the electric field. Because I have a positive charge, everything is spherical symmetric, which tells me that the electric field should be radially out everywhere. Since this is a positive charge, it is not towards the inside, it's towards the outside, it's radially outward. So E dot dl is always less than 0 or equal to 0 along this path. As I go from P2 to P1, if I'm inside this conductor, E dot dl is equal to 0. If I'm inside this empty region, E dot dl is negative. And this integral is nothing but the various contributions E dot dl along this path. Now, if I sum all these contributions, some will be negative, some will be 0. The sum will definitely be negative. So E dot dl integral, as I go from P2 to P1, will be less than 0. This tells me that V of P1 minus V of P2 is greater than 0, which tells me that V of P1 is greater than V of P2. That is the potential at the point P1, that is on the point in the inner surface, is larger than the potential on a point on the outer surface. So this was the answer of our question that we discussed on Thursday. Now, you can also think of it like this. You see, the potential is nothing but you can think of the potential as the potential energy of a unit positive charge. So if you take a unit positive charge at the point P2 and move it towards the point P1, are you doing work on the system or not? Are you doing positive work or negative work on the system? You take this 1 unit of charge and from P2 and carry it to the point P1. Are you doing positive work or negative work? You are the work that you have done. Is it negative or positive? You have this 1 positive charge, 1 unit of positive charge. You take it from the point P2 up to the point P1. Are you doing positive work or negative work? Negative or positive? The work that you are doing, not the electric field. Positive, okay, how many positives, how many negatives? Positives? Negatives? The rest? Wants to walk in the room? Why negative? So? Your friend is saying that the force that you are exerting is in the same direction as the displacement, so you are doing positive work. Now, we don't yet know the potential. Forget about this potential. I mean, this is one conclusion that we have, and this is one way of showing that the potential at P1 is larger than the potential at P2, but we would like to find another way of reaching the same conclusion. Okay, so what is the direction of the force that you are exerting on this positive charge to move it up to P1? What is the displacement? They are in the same direction, so the work that you are doing is positive. That means you're increasing the potential energy of the system, or this unit positive charge is moving from a lower potential to a higher potential. So the potential of the point P1 is larger than the potential of the point P2. Without doing all these integrations, etc. You can always think of the amount of work that you are doing. If you are doing positive work, that means you are increasing the potential energy of the system. If you are doing negative work, that means you are reducing the potential of the system. The potential energy of the system. And the potential of a given point, you can just think of it as the potential energy of a unit positive charge. So just imagine unit positive charge, you carry it from one point to the other point. Are you doing positive work or negative work? Work done by whom? By us. Delta U is equal to delta W. The work that you have done is equal to the change in the potential energy of the system. You are changing using energy to do some work, and that energy is transferred into the potential energy of the system. Or you can say that the change in the potential energy of a given force or the system is equal to minus the work done by the force that is responsible for that potential. Not the work that you have done. Okay. Okay, yes. I'm going from P2 to P1. No, I mean, this is the definition. You start from P2 up to go to P1. This is my final point, this is my initial point. The definition is always a minus sign. Okay, let's do an example. Suppose we already have discussed what happens, what is the electric field when we have two infinite plates. One is positively charged, the other one is negatively charged. Do you remember the electric field? Well, it is 0 here. Here it is, the electric field is sigma over, the magnitude is sigma over epsilon 0. Here it's again 0. And the electric field lines are from positive charge to the negative charge. So what is the potential difference? Let's assume that these two are separated by a distance d. Well, the potential difference, let us just show it by the symbol V only, which we define as the potential of the positive plate minus the potential of the negative plate. This is nothing but the magnitude of E times D, or V is equal to E times sigma over epsilon 0. This is valid for an infinite plate. Now, what does infinite plate mean? And in physics, we never have infinite plates. So if we have an infinite plate, then we have an electric field which is uniform. But what does an infinite plate mean again? So let's say this is the length of the plate. Infinite plate is mainly an approximation when d over L is much less than 1, and we are close to the center of the plate. We are far away from the edges, so we cannot see the edges. Under these circumstances, then we have this infinite plate approximation, which is valid. Now, if we don't have an infinite plate, okay. V is up, yes. Now we can consider a finite plate. Well, let me. Now this time it's not infinite. Now there will be two things that happen if we don't really have an infinite plate. One of them is that the charge distribution will not be uniform. So we will have some charge over here. We will have more charge towards the edges. So the charge distribution sigma will not be uniform. But nevertheless, sigma will be something like sigma 0, some constant, plus some term of the order of d over L. If d over L is small, then sigma will be more or less constant throughout our parallel plates. Now, secondly, now when we said that when we have infinite plates, the electric field line will be horizontal. Let's say if we have infinite plates, we know that the electric field lines will be horizontal because, let's see, if you try to calculate the electric field at this point, there will be a contribution from this segment, but there will always be a symmetric part on the other side. So these two symmetric parts, they contribute there, and their contribution will be horizontal. For every point on my plane, there will be always a symmetrical contribution. So the electric field lines will always be vertical to my plate. Now, if I don't have an infinite plate, if I look at the center, the electric field line on the center will again be horizontal, because for every point over here, there is a symmetrical point on the other side, which will cancel the vertical component. So along this line, through this point, there will be a straight electric field line. Now, as I go towards the edges, let's say at this point, well, there is, let's see, this much part. I have all these points over here have a symmetrical counterpart. So all these the contribution to the electric field from this region will be horizontal. But then I have this remaining region, which doesn't have a symmetrical counterpart on the other side, which will contribute an electric field, which will be pointing somewhere in that direction. But you see, if this is close to the center, I will have a, let me plot it. So you see, this is my image. Now I have these regions, this region. Then there's a symmetrical counterpart, which is over here. Now these two regions, they will create an electric field which is horizontal. This is what the electric field of all these charges will create. For every point over here, I have a symmetrical part on the other side, assuming sigma is almost uniform. But then I have this region, which will create an electric field here, which will be pointing which direction? If this is positive, you say this is positive, this is negative plate. So positive will create an electric field in this direction. The negative plate will create an electric field somewhere in this direction. Will they be equal? If they have equal magnitude, then the electric field will be horizontal. Is the electric field lines horizontal in that point? You see this, I have this region, these positive charges will create some electric field somewhere in this direction. These negative charges will create an electric field somewhere in this direction. Do they have the same magnitude? Well, just make an estimate. I don't want to know the precise ratio, but if one is larger than the other one or not. That's what I want to know. How do you determine whether they have equal magnitudes or not? Just assume sigma is uniform. Let's simplify. Sigma is uniform. It will have some variation depending on at which point you are, but let's ignore it. If sigma is uniform, can you say that the electric field that's somewhere along this line is always horizontal? Okay. No, they have this, why? They have the same area. Yes. Well, I mean, don't look at my sketches. I'm not an artist. Okay. So your friend is saying that, okay, if we consider any point along this line, if I am right at the center, then that point is at the same distance from the positive and from the negative plates. So right at the center, the electric field lines will be horizontal. But if we approach the positive plate, then this point, for example, is closer to these charges than the negative charges. So close to the positive plate, the electric field line will be somewhat pointing upwards because it's closer to the positive charge. These positive charges, not these ones, by the way. If I'm closer to the negative plate, then that point is closer to these negative charges over here than these ones. So then the electric field line closer to the negative plate will be somewhat pointing downwards. Of course, always perpendicular to the surface when it intersects the surface. That means the electric field lines will not be completely horizontal. They will kind of go up and down. Here, the effect will be very small. Now it gets larger at the edges. It becomes even larger, and we even have electric field lines out of these plates. These are what we call the fringing effects. These are also things that we will ignore. Although the plates are finite, since it's finite, we have such effects which do not exist for an infinite plate. We will just ignore these things. We know that at least in the center, the electric field is uniform, and its magnitude, the magnitude of the electric field, is always sigma 0 over epsilon 0. It will be always approximately true because of these effects that we are ignoring, but it will nevertheless give you a reliable result. And we also know that the potential will be sigma 0 over epsilon 0 times d, while the charge density is q over a d over epsilon 0. So this is what the potential difference will be. V will be approximately, of course, it will be q times 1 over epsilon 0 d over a. Now, one thing is that you should know, the potential difference, or the voltage, so-called the voltage across the capacitor, is proportional to the charge in the capacitor. This is what we call a capacitor, a parallel plate capacitor. In the limits that we can ignore these fringing effects, the potential and the charge are related in this form. Now, this is of course a simple example of a system where we have some separation of charges. We create some potential difference, and at least in this system, the potential difference that we create is proportional to the charge. And that proportionality constant we usually define as the capacitance. Or you can solve for the charge in the capacitor as the capacitance times the voltage. Now, basically, a capacitor is anything that kind of either separates the charges or it stores some amount of charge. But anything that has these properties we call a capacitor. You can take, for example, some arbitrary conductor and some other conductor. This is a capacitor. Your two friends sitting over here, they form a capacitor. They are conductors, so they are capacitors. You can just put charge on them. They can store charge. The charge will be moving around. And eventually it will settle somewhere, creating some potential difference. And the potential difference that you create between your friends will always be proportional to the charge that you put on them. You take some plus 5 coulombs from one friend and put it on your other friend. So you know the Q, you can measure the potential difference. They will always be proportional to each other, and the proportionality constant will always be C. Now, of course, if you take just 5 coulombs from Serjan and put it to your other friend, one will be positively charged, the other one will be negatively charged. The 5 coulombs is a huge charge, so they will feel a huge attractive force between them. And so, I mean, their configuration will change. They will just fly to each other. And so the capacitance will, of course, change because you have basically breaking the capacitor. But if you assume that everything, the conductors are fixed, they do not move, they are not allowed to move, your geometry doesn't change, in such a case, the capacitance will be a constant. It will not depend on how much charge you put on your system. Questions? Well, for a general system, let's say what is your capacitance, your two? Well, if I put some charge Q, then I don't know the potential. I mean, there's no way I can calculate it. You are just you have complicated shapes. So in that case, what should I do is I should put some charge on you and measure the potential difference. Then the ratio Q over V will tell me what is your capacitance. And the only way I have two ways. Either I measure the capacitance or I calculate it numerically. I will not be able to obtain any simple analytical expression for your capacitance. Now, this is one example where we can actually calculate the capacitance analytically. Of course, making these assumptions, we can calculate it. Without these assumptions, even this is quite a complicated problem. So in this case, the capacitance, this is what we had. And we know that V is defined as Q over C. This tells me that C is equal to epsilon 0 A over D. Now, what does this tell me? How can we interpret this capacitance? If a system has a large capacitance, what does it really mean? Now, if a system has a large capacitance, even if you put a very large charge on your system, it will create a very small potential difference. A very small potential difference will mean that your system will create a small electric field. And in fact, if you imagine, you have probably seen all these electrostatic generators where you have these electric sparks going from one to the other one. Or you have probably been electrocuted by your car, especially on dry days. You hold the doorknob or your car, and then there is a spark. Hiç çarpılmadınız mı? In the dorm, especially if the floors are made of plastic, you have a plastic slippers, then you will feel it quite often. You just touch a metal and you are shocked. There's an electric shock. Well, you need, for 1 millimeter of an electric spark to jump over 1 millimeter, you need approximately 10,000 volts. Once there's 10,000 volts of potential difference, you get these shocks for the atmosphere, for air. That is the threshold for the so-called electrical breakdown of the material. So there's an electrical breakdown, and you have this shock, which also happens in the thunders. Now, every material has kind of a limiting value of an electric field that they can resist. If the electric field is much higher than that critical value, then the current will start to flow through it, because you are basically breaking the bonds between the atoms and the electrons. You are breaking off the electrons, which then start to move. But if you want to store an some charge, separate the charges, you have to make sure that the electric field that you are creating is lower than that breakdown limit. That is, your potential difference is lower than a given limit. A material that has a large capacitance can store a large amount of charge before reaching that critical value. So that's what you would expect. It has a large capacity to collect electric charge before the electrical breakdown. Now, what other electric capacitances can we, is there any questions up to now? Why do we call it the capacitance? It mainly measures how much electric charge it can carry before electrical breakdown. A material that has a large capacitance can carry a large amount of electric charge before the breakdown. Sure. This whole system you can treat as a dipole. In fact, you can even calculate the dipole moment if you know the charge distribution. If you assume it to be constant, you can just divide it into very small dipoles, sum all the dipole moments of that very small pieces, and you know the dipole moment of the whole system. Let's calculate the cylindrical capacitor. So you see, if you look at the definition, if you want to calculate the capacitance of a given system, what you have to do is put some charge on the system, calculate the potential difference created by that charge, take the ratio that gives you the capacitance. So that's what we should do. Well, you see, you can say the capacitance is kind of the measure of the maximum that you can store. No. The capacitance is a constant. The capacitance of a given system is always a constant. Remember when we were discussing this chapter on conductors, when we said that, okay, if you put some charge on one side, then there's no electric field in the conductor, because if you put some charge at some point out of the conductor, the charges inside, they just split, creating an additional electric field which cancels the applied electric field. And there were all these questions asking, what if we put a huge amount of charge? Well, eventually the system breaks down. Every system breaks down. Now, a system that has a larger capacitance will break down at a later time, keeping everything fixed, everything else fixed. If you don't change anything else, we will see, for example, when we discuss the dielectrics increase the capacitance of a given capacitor of the same geometry, mainly because they reduce the electric field. The maximum electric field you can build up in a material without electric breakdown, that is, without that material becoming a conductor, is limited. Of course, you don't have to charge the capacitor until you have the electrical breakdown. That's a huge, in most cases, that will be a huge charge. The properties of the material. For example, a conductor has zero. It's already a conducting. You don't need any electric field to start it conducting. It will be the microscopic properties. When we discuss the dielectrics, ask again. Sure. We can build capacitor even from two of you. Other questions? Okay, so the cylindrical capacitor is basically we have two cylinders, two conductors of cylindrical shape, one inside the other one. So let's say the inner one has radius A, the other one has radius B. So what is the capacitance? Now to calculate the capacitance, we first have to put a charge on the system. Well, this is a conductor, it's quite symmetrical, so whatever charge we put, it will be distributed uniformly over the surfaces. So let's see if we look at the top view, this is A, this is B. If, let's say, we put some positive charge inside, and then in the inner surface of the outer shell, we will have some negative charges accumulated. So here inside we have a plus Q charge, outside we will have a minus Q charge. Yes, the surface densities of the charges will be different. We will have a larger surface density in the inner cylinder than in the outer cylinder. Because just as you said, the inner cylinder has a smaller surface area. How can we calculate the electric field? Well, we have put some charges Q, plus Q on the inner cylinder, minus Q on the outer cylinder. Now we have to calculate the potential difference of this configuration. To obtain the potential difference, we have to calculate the electric field. To calculate the electric field, we can use the Gauss Law. So what kind of a surface would you like to have? How would you like to use the Gauss Law? Circle. Where? Here. You mean here? Well, that is basically a cylinder, no? Why do you choose such a Gauss surface? Okay, well, I mean, we would like to find the potential difference, V, which will be in the integral of E dot dl. But what is the electric field? That is now the question. First, we need to find the electric field so we can determine the potential difference using the definition of the potential difference in terms of the electric field. Now, to determine the electric field, your friend proposed to use the Gauss law. And he said that, okay, we can choose such a cylindrical Gauss surface and apply the Gauss law on this surface. Now, my question is, why this surface? Why not a sphere, for example? How? I mean, the electric field line will not have this cylindrical shape. Okay. This one. Okay. I'm looking at them. And I keep looking. Why? The same total charge. Yes. The inner cylinder has a total charge plus Q, the outer cylinder has a total charge minus Q. We have? Okay. Okay, I mean, you say, you can think that something is right, you can believe that something is right, but that doesn't mean that is right. How do you prove that something is right? And by the way, what they say is wrong. I mean, they are correct up to an approximation. Okay, so we have such a, you mean such a Gauss surface. How do you know that the electric field here is 0? So, well, I have a dipole which has a minus q, plus q. I can take this Gauss surface, the integral will be 0. You see, no, hold on. How do you know that the electric field is 0 to start with? Okay, fine, but that doesn't mean that the electric field is 0. I'm just giving the example of a dipole. The dipole has a total charge 0. Nevertheless, we have seen that it creates an electric field, it creates a potential difference. It creates a potential, although the total charge is 0. No? You see, for such a surface, Gauss law tells me that E dot ds is equal to 0. But this doesn't necessarily mean that E is equal to 0. It doesn't mean that. Electric field might just get out of the Gauss surface at some point and get in from some other point. This just means that electric field is pointing towards the outside of the surface at certain regions and towards inside of the surface in other regions. This only states that. It doesn't tell us that the electric field is 0. We don't know it. I mean, without additional ingredients from this one, we cannot conclude that the electric field is 0. We need additional information. Yes. Why? I mean, that would make the calculation easy, but I mean, how do you know that such a Gauss surface exists? I mean, are you sure you can always do that? Okay. Let me also compare your try to this case. Will it? I mean, you see, this answer is approximately correct. But why? That's my question. How do you know that we should choose a cylindrical Gauss surface? That is more important than the correct answer. Yes, your friend has something. Yes. No, Ahmed was saying something. What do you mean by symmetric? What do you mean by symmetric? What kind of symmetry are you talking about? I mean, okay, so I take this cylinder, I rotate it like this, nothing changes, right? So the electric field also shouldn't change. That's not the complete answer, by the way. So, for example, I can have, let's say this is my configuration. Just look at it from the side. This is the outer cylinder. This is the inner cylinder. For example, the electric field line, the electric field at this point might be looking like this, and the electric field here might be looking like that. So, I mean, just imagine the electric field. This is my cylinder. The electric field lines at certain points, let's say, they all point like this. This has the cylindrical symmetry. If I rotate it, nothing changes. So if the electric field line fields are looking like this, would you still choose a cylindrical Gauss surface? You were saying that we should choose a perpendicular surface. Is a cylinder perpendicular to this one? Why sphere? Okay, you say in the questions that we are discussing, we are always taking the simple cases that can be solved, like the cylinder, the sphere, and the planes. But in nature, they don't have to be. So it's more important to understand why you can choose one surface and not some other surface. I mean, in all the questions we have, you will be choosing a Gauss surface that is either a cylinder or a sphere or a cylinder. No, a cylinder or a sphere. That will be it. That will be the only choices we will have. So, I mean, if you need to choose a Gauss cylinder, you will get 50% of guessing the right answer. But you might have cases where you cannot apply the Gauss law. So you cannot really choose the surface. So you have to be able to tell why we choose one surface and not some other surface as our Gauss surface. Now, in this case, why do we choose this cylindrical Gauss surface? Any other additional comments? Yes. This one. Now, in this one, this is completely symmetric. This has cylindrical symmetry. It doesn't have any problem. But your friend is kind of approaching. I mean, you can think a limit, for example, a limit when the radius of these cylinders becomes very, very huge, very, very large. So in that limit, I mean, if you look at a region, it just looks like a parallel plate capacitor. So that can give you some idea. That can also give you an idea why this is also symmetric. I mean, we had already discussed such electric fields, the analog of such electric fields in a parallel plate capacitor. Remember, we had this weird name? Yes. We have these fringing effects also in this cylindrical capacitor. So those fringing effects will cause the electric field close to the upper or the lower part of the cylinder to point either upward or downward. I mean, it will just go up and down, up and down. So we will have these things. And as long as we have these things, you cannot choose a cylindrical Gauss surface. Now you can always choose a cylindrical Gauss surface, but it will not help you in your calculation. It is true, it will be true, but it will be useless in our case. But we will, just as in the case of the parallel plate capacitor, here we will also make an assumption. We will assume that these cylinders are almost infinite. Now, if they are almost infinite, then the electric field lines, they have to be horizontal. If they are almost infinite, imagine this almost infinite cylinder. Imagine putting a mirror over here, nothing changes. The mirror image is the same. So it should be the same for the electric field. So the electric field cannot have any vertical component. It has to be horizontal. Now, secondly, your friend says that it has to have rotational symmetry. So if you take this cylindrical symmetry, if you just rotate your system around the axis of your cylinders, nothing changes. So should be true for your electric field. So for example, if you take any point somewhere over here at a distance rho, then the electric field will only depend on rho, its magnitude, and it will be only in the outward direction. So this is this should be the form of our electric field. And now we can say that what is the geometrical shape of points in which the electric field has the same magnitude, that is the cylinder. So rho is equal to constant. These are the points on which E is, the magnitude is constant. Furthermore, as your friend pointed out, on these points, if you just imagine the surface formed by all these points, which is the size of a cylinder, the area vector, that is the unit vector pointing out of these areas, is in the same direction as the electric field. So it will make our calculation quite easy, much more easier. Now we will continue from here in the next hour.